Right.
That worked.
Yeah, you can start.
All right. Well, thank you. Well, thank you for the invitation. Hopefully, we can all gather in Paris again soon and do this in person next time. But happy to be here with you all. Uh, I was chatting with Eric prior to getting started, and he mentioned that a large number of the participants at the meeting come from a theoretical physics background. Well, I also come from a theoretical background. I actually started out in alternative theories of gravity and quantum gravity, uh, and I was working on. I spent time in Cambridge in Hawking's group working on quantum gravity, quantum cosmology, and I became increasingly interested in how we might test some of these ideas in the universe. So I first got into cosmic microwave background observations, trying to determine if the universe had a non-trivial topology, and that led to some analyses with the WMAP data, and that really was my start into actually working on the data side. But I think that with my background from a theoretical background rather than an experimental background, I've always taken a fairly theoretical approach, mathematical approach to the data analysis, and have used that to develop new techniques. So, uh, first of all, I have some resources here. You'll get these slides, so you don't have to write all of this down. Um, Three papers that I think are good resources. One was a LIGO-Virgo collaboration paper, the guide to LIGO-Virgo data analysis, and um, I was one of the lead authors of that, along with several other people, including Jolyon Crichton, who I have down here, down as one of the book recommendations. And I also previously gave a course at SASFE, and so I've even got a Dropbox link so you can download that chapter for free if you like. Let me know if that link no longer works. I didn't check it recently. There's a review paper I wrote with Joe Romano, nominally on detecting stochastic gravitational wave backgrounds, which, ironically enough, I'm not really going to talk about so much in these lectures. But that, despite its title, that review article actually covers a lot more than stochastic gravitational waves. And then, yeah, and then I mentioned the books, Majore's book and then the Crichton and Anderson book, all good resources if you're interested in learning some more. So, what I plan to cover over the next 2 days, a lot of things, and we'll see how far we get. I'll start skipping things if the timing doesn't go well. And if you have questions, please jump in at any time, put them in the chat, and Eric will stop me to ask those questions if I don't see the chat. So I'm just going to run through some of these and get you hopefully a picture of gravitational wave data analysis. I will talk a little bit about I work actually across the sort of pan-spectral gravitational wave data analysis. I'm, as Eric said, member of the LIGO collaboration, LIGO-Virgo effort, and for a long time I've also been involved in LISA. I'm currently a member of the NASA LISA study team, and I'm also a member of the nanograv effort for pulsar timing, and one of the nodes in the nanograv Physics Frontier Center here in the US. So one of the things I like to emphasize in that article with Joe, the title of it is like a unified treatment. One of the things I like to emphasize is that a lot of the tools and a lot of the math behind the analysis for pulsar timing, LISA, and LIGO, and Virgo, it's really all the same. So they're very different instruments, but the mathematics of how they detect gravitational waves and a lot of what we do is the same. So all of this is fairly, can be used across that spectrum. So let's start with detector response functions, and this is a little animation that the LIGO collaboration made associated with the first detection of gravitational waves, and vastly exaggerated wobbling of the Earth and vastly slowed down gravitational waves coming through here for the very first gravitational wave signal that we detected, GW 150914. And if you look at the data in the detectors, so we've got this gravitational wave coming in from the direction indicated. So it's reaching the Livingston detector. It encountered the Livingston detector first, and then it continued propagating along and then reached the Hanford detector in Hanford, Washington. And you can see here the gravitational waveforms that you get in the Hanford and Livingston detector. You see that they're offset in time. The time delay is approximately 7 milliseconds. The total light travel time between Livingston and Hanford sites is about 10 milliseconds. So this really was coming in at an angle that accentuated that time delay. If a gravitational wave came from directly above the United States, say over Kansas, then the time delay would be 0. So this had quite a large time delay. There's a phase shift. It's not quite a flip of pi, but it's about 2.9 radians. And also we see that the response in the Hanford detector is about 1.2 times larger than the response in the Livingston detector. And all of this comes down to the antenna response. So this is how the detectors are responding to the gravitational waves, leads to these amplitude and phase shifts. And of course, the time of arrival gives you the time delays. And I'll also be talking a little bit how this then allows us to localize where these gravitational waves are coming from. And but I want to just take you through a little bit of the math behind these responses. So all of these gravitational wave detectors, whether it be the ground-based LIGO and Virgo detectors, space-based LISA detector, or the pulsar timing arrays, these are all time-of-flight detectors. Historically, we also had acoustic or bar detectors where we were looking for the mechanical response of, say, an aluminum bar, where it would be sort of stretched and squeezed by the gravitational waves. But those are no longer really competitive with the laser interferometers. And so now all of the techniques that are being used really these days for gravitational wave detection are really time of flight. How long does it take photons to go from one location in space-time to another, and it's perturbed by the passing gravitational wave? So for example, pulsar timing is the simplest example. You have a pulsar, rapidly rotating neutron star, so you have this beam of radio waves that, like a lighthouse, is sweeping around, so you get these pulses arriving at Earth, and if there are gravitational waves in the intervening space-time, those pulses might arrive a little earlier or a little later than they otherwise would. So that's the simplest kind of time-of-flight detector. One of the earliest forms of gravitational wave, at least searches, not detection so far, was spacecraft Doppler tracking, where radio signals would be transponded from a spacecraft and back to the Earth, and again, looking for the time of arrival fluctuations that might occur. And this was a Doppler response, so looking at the fractional change in the frequency of the radio signal. So that was then the time derivative of the time delays caused by the gravitational waves propagating in this perturbed space-time. And then finally, you have the laser interferometers, where we send light along two paths and then recombine it. So we have a beam splitter and then we recombine. And the output screen, as you would have heard from David Shoemaker, we look for phase shifts. and so it's the time delay multiplied by the angular frequency of the laser. And because we can't build perfect lasers that have perfectly stable frequencies, this forces it into something like a Michelson topology, like we see here, so that the laser phase noise actually cancels as we recombine these beams, because any change in the frequency would be degenerate with a change in the light travel time. So since we don't have perfectly stable lasers, we have to use a Michelson setup to cancel that otherwise large laser frequency change or phase noise. I mean, it's very small, but relative to the gravitational waves, it's a very large effect. So what it comes down to, if you want to calculate the response of a detector, is you just need to calculate the time of flight of photons in a space-time perturbed by gravitational waves. Now, the main difference between, say, the ground-based, space-based, and pulsar timing is the regime in which we're operating in terms of the length of the arms versus the wavelength of the gravitational waves. And so I've got a table here taken from that review article with Joan Romano. In the case of LIGO, the arms of the detector, which is sort of kilometer scale, are very much shorter than the typical gravitational waves we're detecting, which have wavelengths in the sort of thousands of kilometers. For LISA operates kind of right in the mid-range here, where the wavelengths of the gravitational waves range from being shorter than the arm lengths to longer. So it kind of spans this regime. Whereas pulsar timing, the gravitational wavelengths are very much shorter than the distance between, say, the Earth and the pulsars, which are typically at kiloparsec, like 1 or 2 kiloparsec kind of distances, and the wavelengths we're looking for are significantly smaller than that. So that's the only real difference between the three. The math is the same in all cases, as you'll see shortly. So to do these calculations, all you have to do is take, say, a metric, just say Minkowski space, perturbed by a gravitational wave. We can organize our axes, so the gravitational wave is traveling in the z direction. Make the usual change of variables to t minus z and t plus z, and then the metric has the form where you now see that it depends, the gravitational wave is traveling in the positive z direction, so it only depends on u, and you see that the metric then is independent of v, it's independent of x, and it's independent of y. So that means you're going to have symmetries, killing vectors, and that makes it very easy to solve for the photon geodesics in this space-time. So the calculation just comes down to calculating the time of flight of photons in this perturbed space-time. If you like, you could do it in a different background space-time, such as like a Schwarzschild background. It doesn't change the math too much. So, as I mentioned, there are 3 killing vectors associated with the symmetries of this space-time. You've also got the normalization condition that these are null geodesics. So that gives you 4 constants of motion. So you've reduced the geodesic problem to quadratures, and so it really just becomes an algebraic problem then solving for the time delays. So I'm just going to walk you through a little bit of the calculation, and you can read the details. I have a paper where I talk about this for the case of LIGO and LISA, and then the original usage of these symmetries and Killen vectors to do this calculation was a paper from Estabrook and Wahlquist back in 1975, where they were calculating the response for spacecraft Doppler tracking. So it was doing the Doppler version of this. So you start just by considering the unperturbed path of a photon in this space-time. So for example, starting at the origin of your coordinate system and then propagating to some event with coordinates t, x, y, and z. I've already put in here that t is just L because for the unperturbed space-time, the trajectory is just a straight line here. Delta lambda is the change in the affine parameter, and so the constants of motion in this unperturbed space-time are given by just this distance, x, y, and z, just divided by that lapse. And the nice thing about the TT gauge, as I'm sure you know, is that if you have a free-floating mass sitting at rest initially in that coordinate system, then it stays at rest. It stays at that same coordinate location as a gravitational wave goes through, because in effect, the transverse traceless gauge has sort of absorbed the gravitational waves into the gauge conditions. So it sort of hides the gravitational wave to a certain extent, but it makes the calculations very, very simple because the masses stay at the same coordinate locations. So that's just the unperturbed trajectory, and then you perturb around that. So now the trajectory gets perturbed because you've now, and these are all going to be of order h, where that's the gravitational wave. So then you just go through and calculate these perturbed equations, and the constants of motion shift a little. So the conserved quantities shift over, and then you solve for the perturbations, just expanding around the solution with h of 0. And to leading order, you find, for example, that this constant of motion Sx is given in terms of the plus and cross polarizations and the 4 velocities here of the masses, and then you integrate that up, and you get that the perturbation in this constant of motion is given by this antiderivative of the plus and cross polarizations, and then that's the full expression, and then you put that into the null condition, and you get that the perturbation in the time of arrival is given by this expression here. And here we were working in a particular coordinate system where the gravitational waves were going in the propagating in the z direction. So you see, since it's transverse, we've got the antiderivative of the gravitational wave metric perturbation here in the xx, yy, and xy direction, and we're calling the xx h plus and hyy minus h plus, and then hxy is h cross. So this was all done in a particular, with setting up our axes so that it's along the propagating along the z direction, but you can do the sort of coordinate independent version of this, where now I have the gravitational wave tensor, the antiderivative of the gravitational wave perturbation here. A is now a unit vector along that arm, and this double dot is just the full contraction of this tensor with this tensor. And on the denominator here, we're getting we have a term that goes as the propagation direction k dotted into the arm direction. So this then is the expression for the time delay along one pass in space-time, so just between two locations. And once you have that, you can now calculate the response for any kind of gravitational wave detector, because if it's pulsar timing, well, you're already done, because that's all you need to know. If it's spacecraft Doppler tracking, you have to do the return path. If it's something like a LIGO interferometer, you have to consider the paths up and back the two arms, but it's all the same calculation as what we've just done. So once you've calculated the time delay along one path, you just put together the full response by combining this expression over and over. You can introduce here for the gravitational wave tensor a basis where I have a plus and cross basis tensor here, written as epsilon plus and epsilon cross. And this then allows you to do things like calculate the antenna patterns and things. So if we now do a general coordinate setup, so what I'm going to do now is consider an interferometer where I'm going to use a coordinate system attached to the interferometer. So the arms of the interferometer are going to be along the x and y directions, and the z direction is going to be perpendicular to the plane of the interferometer. And we'll have a gravitational wave, which is in the n hat direction on the sky, so with sky coordinates theta and phi. And then we have we set up coordinates u and v spanning the plane orthogonal to the direction that the gravitational wave is coming from. Of course, the propagation direction, k hat, is in the minus n hat direction. So this is the gravitational wave is propagating to us like this. And our detector tensor, we can set up in our detector frame, the plus and cross polarizations for this frame are given by these expressions. So we have the tensor product of the u hat vectors minus the tensor product of the v hat unit vectors, and then similarly this mixed expression for the E plus. Now the gravitational wave doesn't know that we set up this UV coordinate system. This is set up relative to our detector frame. The physics of whatever's producing the gravitational waves is going to set up preferred axes in the source frame, and so the principal axes for the plus and cross polarizations of the source frame, P and Q hat here, are going to be rotated typically by some angle psi relative to the frame that we've set up as our reference frame. So these tensors epsilon, plus, and cross are given by these combinations. Since we're rotating a tensor, we get cosine 2 psi and sine 2 psi. If you're rotating a vector, of course, you would just get cosine psi and sine psi. So because it's a rank 2 quadrupole here, it's coming in with the 2 psi, sine 2 psi. So that's where the polarization angle, it's just because we have we don't know in advance what the principal axes of our gravitational wave are. So we've got the polarization angle and the sky location. Those are the quantities that enter into the gravitational wave response. So for example, if we were to try and calculate then the expression for the this time delay in something like a very simple Michelson interferometer, as you know, in reality it's more complicated than this because we have these Fabry-Perot cavities in the arms. So you really have to go through and do the calculations as you find in those textbooks that I reference, where you can see the impact on the laser phase shifts in these cavities. But this perhaps is a little bit more appropriate to say a LISA type setup, where it's just a true Michelson type setup of just passing down one arm and back and then getting compared. So in this simple Michelson topology, the time delay is made up of the combination of the time that it takes to go from 1 to 2 and then 2 to 4 minus the time it takes to go from 1 to 3 and 3 to 4, right? So you put in the expressions from the previous slides, and if you're working in the long wavelength limit where the gravitational waves are much longer than the arms, then this simplifies down to just this this combination here. If the arms of the detector in the A hat and B hat direction, you just get A minus, A tensor product A minus B tensor product B, and that gets contracted in with the gravitational wave. Those antiderivatives essentially got undone by the differencing here. That kind of works like a finite difference operation. So you end up just with this detector tensor contracted in with the gravitational wave. And if we recall that these are, the gravitational wave can be written in terms of the polarization tensors and then the plus and the cross polarization amplitudes here as a function of time, then what you get is the contraction of these basis tensors here into these polarization tensors. So that's where, and it's very simple, you can check these calculations yourself. So you can just calculate what are the inner products of A and B are in the X and Y directions here. So you contract those in with these expressions, and you calculate these out, and you get just these combinations of sines and cosines of the sky location. And then you put it together, also including that polarization angle. And you can then write it in what I think a form that you've seen before for ground-based detectors, where it's a antenna pattern factor F plus multiplying the plus polarization, F cross multiplying the cross polarization, and just putting together the expressions from the previous page, you get that F plus and F cross are given by these expressions here. So those are the antenna patterns that you calculate for, say, a ground-based detector like LIGO. And in the low frequency limit for LISA, these also hold as the antenna patterns. So there's the math. It's all pretty simple trigonometry, really, to get the antenna response for the LIGO detectors. And it was just photons propagating through a perturbed spacetime. So for what if I was to plot these out, the plus and cross polarizations have these sort of peanut shapes, and especially when you combine them, the sort of polarization average response, you get this in the plane orthogonal to the detector, both up and down, you get the strongest response. And then in the plane of the detector, you get some much reduced responses at 4 locations, 4 little indentations here, but then there's still directions even in the plane of the detector, so coming in with the gravitational waves coming in parallel to the plane of the detector, you still get a decent response in 4 directions as well. So you've got this dimple type geometry here. And those phase shifts and amplitude differences that I showed earlier for GW 150914 just had to do with the antenna patterns for LIGO Hanford and LIGO Livingston being oriented slightly differently, and that's what put in these phase and amplitude shifts. Of course, the time delay just came from the propagation of the gravitational waves across the Earth. So if we look at the terrestrial network, we have the Hanford detector, the Livingston detector, we've got the Virgo detector just outside of Pisa. In the not too distant future, we'll have a detector in India, one of the LIGO detectors being sited in India. And then we have the CAGRA detector, which has joined now with the LIGO and Virgo detectors to form a worldwide network. It's not yet, the CAGRA detector is still working up to get up to a comparable sensitivity, but hopefully in our next observation run, we might get some input from CAGRA. So I'll just superimpose these antenna patterns. So for Hanford, it's most sensitive directly above the Hanford detector and directly below. Gravitational waves don't care about going through the Earth. The Earth is just transparent to gravitational waves. And then you can see these nulls dotted around the Earth here. Rotates around a bit for the Livingston detector, but quite similar, quite a good overlap with the Hanford detector. The Virgo detector really samples quite a different locations on the sky, and that has some advantages. The Indian detector, yet another sampling. It will be very helpful when we have the Indian detector, because adding this coverage and also time delays measurements, and then CAGRA, when it reaches comparable sensitivity to the LIGO and Virgo detectors, will also be very valuable. As you'll notice, all of these detectors are in the northern hemisphere. It would be very nice to have a detector in the southern hemisphere, but unfortunately that's not in the immediate plans. In Australia, we might be putting in a high frequency detector to try and measure the final stages of neutron star mergers, but that's still in the early planning stages. So just a little bit on how we use this information to figure out where the gravitational waves are coming from. So if you just have the two LIGO detectors, like we did initially when GW 150914 arrived, that time of arrival defines a circle on the sky. So I see a question in the chat from Chiara. Don't these sensitivity regions vary over the year? No, not in a. I was showing it in Earth fixed coordinates. So of course the Earth rotates around, but the detectors are, rigidly, rigidly connected to the Earth. So those patterns are made fixed. Of course, the Earth rotates, so at different times of the day, we're more sensitive in certain directions, but those patterns don't change over the year because I was using Earth fixed coordinates. And then I see another question: what's the issue with the northern hemisphere? Don't gravitational waves travel through the Earth? Absolutely, they do. In fact, that first gravitational wave signal, GW 150914, kind of came through from through the Earth up through like Africa, but it means that we don't have anything in the southern hemisphere in terms of these triangulation lines. So it really helps with triangulation if we had something. See, we want something outside of that plane in the north. If we had by putting them around the Earth, we're doing very well on our sort of east-west triangulation, but we're not doing nearly so well on our sort of our polar angle, right? So if we had ones that were separated by a greater amount in the polar direction, then we would narrow down that direction on the sky a lot better. We're doing very well in the azimuthal direction because we have them dotted all around the Earth, east to west, but if we had north-south, then we would actually pin things down better in the north-south direction. So with a single pair of detectors, it narrows to get the same time of arrival. That narrows it down to a ring on the sky. So there's a ring of locations on the sky that will give you the same arrival time at the two detectors. So if you have now a third detector, such as Virgo, that defines a new ring on the sky. And then you get two intersection points. The yellow dotted line here is where the gravitational wave is actually coming from. And so anywhere on this red line would actually have given you the same arrival time along this axis here, the red line here. Whereas now if we add in Virgo, we get a new line, and so that actually narrows it down to two locations on the sky, which you can also combine with the antenna patterns. Then that can kind of break the degeneracy between whether it's at this intersection or this intersection. So there's going to be an antenna response that's different in the two locations, and that helps. So the relative amplitude that we see in each detector combined with these times of arrivals is how we triangulate the sources. And just here's an example where if we just had the Hanford detector and we had a gravitational wave signal coming in, then it would be localized to these big sort of blobs which really follow the antenna pattern of the Hanford detector. So not really very useful for doing any kind of follow-up to try and find an electromagnetic counterpart. If you combine the Hanford and Livingston detector, you get this characteristic pattern here. So this is the line of equal time delay projected into a Molway projection on the Earth. And you see that it's weighted by the antenna pattern. So while this line extends all the way around the Earth, because of those lobes of the antenna pattern, it really just lights up two locations along the ring. And this is very characteristic of what you see from a lot of the detections that we announce with LIGO and Virgo. We often really only have say, two detectors working at a time, or Virgo's maybe not quite as sensitive sometimes as the LIGO detectors. So we very often get these kind of rings that are just lit up in two locations, so quite large regions then to follow up to look for an electromagnetic counterpart. Now, when you combine Virgo in this particular simulated case, we then get this nice bullseye because the corresponding location, the amplitudes weren't correct. So this really bullseyes that source down to this location, and now we're in much better shape for being able to do some kind of electromagnetic follow-up. I made these slides maybe for this particular simulation probably 10, 15 years ago. And what's interesting is it's very similar to what happened in reality then with GW 150914, sorry, GW 170817, the first binary neutron star merger. So here is the sensitivity map. So what's been done here in making this picture is the antenna patterns of the two LIGO detectors have been added together. So this is kind of the combined LIGO sky map, and still it's kind of similar to the pattern you get for one of them because they're quite close together. So it has these nulls here where the response isn't very strong, and then we've got these time delay rings. So this is the different time delay rings from the different pairs of detectors. And I'm also showing the Virgo time delay ring here as well. And so it narrowed it down to these two possible sky locations, including Virgo. But then when you look at the Virgo antenna pattern, you see that one of those sky locations is in a sensitive region, a very sensitive region for Virgo, and the other one is in a relatively insensitive direction on the sky for Virgo. And because the signal was so weak in Virgo, pretty much not discernible, that ruled out this sky location. Because if it had been at this sky location, we would have seen a much more significant response in the Virgo detector. So this was quite a loud signal, and Virgo would have seen it quite clearly if it had been at this sky location. So the fact that Virgo didn't see it means that we're able to eliminate that sky location and narrow it down to this one here. And then the contours actually of that, including the antenna pattern weighting, shows you the uncertainty contours that we then had to give to our electromagnetic counterpart hunters to then look to find the host galaxy for this event, which of course they did, and that was the first definitive detection of a kilonova, and all the great science that came out of that. And so here Virgo played a very important role by not seeing the gravitational waves. It ruled out this location and narrowed it down to this location here. So that was all for the working in the low frequency approximation, long wavelength approximation. Let's see. I see a question in the chat. Yeah, so the current gravitational wave experiments, I don't have a plot of it, but if you were to combine, I've seen plots made like that where people show the combined antenna pattern coverage of LIGO and Virgo. It does cover the sky pretty well. What you really should be doing, though, to make a plot like that is not just combining the antenna patterns, but doing a noise-weighted combination that takes into account the different sensitivities of the detectors. So that then currently weights the LIGO contribution more heavily than the Virgo contribution, just because the LIGO detectors are still a bit more sensitive. So the overall combined noise-weighted antenna patterns actually look a lot more just like the LIGO antenna patterns. That's not to say that Virgo hasn't, been a major contribution on quite a few of the discoveries. And in the case of GW 170817, it was critical to the finding the counterpart. And we've certainly had multiple events where there's definitely a signal seen also in Virgo, but still it's, when you combine it all. Now, once Virgo reaches the same sensitivity or close to the same sensitivity as the LIGO detectors, will have very good sky coverage, pretty much full sky coverage with a couple of maybe weak spots, which will then be covered by CAGRA as CAGRA sensitivity improves. And certainly by the time we have the Indian location for one of the LIGO detectors, we'll have really pretty much 4 pi steradian, almost equal sensitivity in every direction on the sky. So that's something that we're heading towards. And something that I'm not really probably going to talk about is the once you have more detectors, you can do things like test the polarization content of the gravitational waves much better, and actually see if it's just the 2 polarizations predicted in Einstein's theory, or whether there's any indication of additional polarization states which you generically get in alternative theories of gravity. So having more detectors is good for many, many reasons. So going on to, that was all in the low frequency approximation. Yeah, and it is similar to AHT. This is a sort of a, it is in the radio world, this is sort of synthetic aperture. We by coherently combining the detectors, they really operate as a single global detector, is a good way to think about it. All right, so beyond the low frequency approximation, you get some interesting effects. And when I put this together just for a single arm, you've got your sort of antenna pattern term out the front, which is just going to come out as sines and cosines of the various sky angles and polarization angles. You have this cardinal sine function, which is a finite arm length correction. So this actually decays for frequencies that are, well, for wavelengths, sorry, that are shorter than the arm length. You can either do it in frequencies or wavelengths. This then decays as 1 over frequency, so you have this fall off in sensitivity once you get outside of the low frequency approximation. That's the cardinal sine function there, and the overall phase here is then just referenced in this case to the midpoint of the arm. This expression is useful for both pulsar timing and for LISA. In the case of pulsar timing, where I've got this geometry here, where I've got a pulsar, which is our detector. So our detector arm is in the A-hat direction here. We have some supermassive black hole binary off in the N-hat direction. I'm even including here possible corrections due to the non-plane wave nature, perhaps, of the wave fronts over these kind of distances. But basically, what it means is the antenna pattern, and this is the case where the product of the frequency times the arm length is 10, and you see this interesting corrugations now in the antenna pattern, and that's coming from these nulls caused by this cardinal sine function. So you get this much more, much richer antenna pattern than what you have at low frequencies. And the same goes for LISA. Here is what the LISA antenna pattern looks like in the low frequency limit, and it looks just like the LIGO antenna pattern. And so as the spacecraft orbit around the sun, the plane of the detector is changing throughout the year, and so you see the lobes of the antenna pattern get swept across the sky. And so for LISA, the way that we can, since we only have, well, we may be joined by a Chinese detector potentially, which would improve sky localization. But if we just have the LISA detector, then we're going to be relying on this amplitude modulation as the antenna pattern sweeps across the sky, but also you essentially get time delays, or if you want to think about them as Doppler shifts, because as the detector moves around, if it's a long-lived source, then you're measuring it at different times of the years. You can put together essentially those time delays, or equivalently, just because of the motion of the detector, you're getting Doppler shifts, if you want to think about it that way. So it's a combination of frequency and amplitude modulation is how we infer sky locations using LISA. Now, that's true for the low frequency response, as you'll see in the next slides. As you get up to higher frequencies, and once the wavelengths start fitting inside the array, you really start getting time of arrival information. When did the gravitational wave reach one of the spacecraft or the other spacecraft? So then it becomes much more like the LIGO-Virgo type triangulation, because you actually get time delays, measurable time delays across the spacecraft, because these are about 2.5 million kilometers apart. And so those time delays for short wavelength gravitational waves actually give you much better angular resolution. So as you go up in frequency, so if you're down at 1 millihertz, the LISA antenna patterns, this is now in the detector frame, so this is the Z direction now is orthogonal to the plane of the detector. You see you're most sensitive above and below the plane, and then you've got those nulls along the equator, along the plane of the detector. And so at low frequencies, it looks just like the LIGO response. As you go up in frequency, it starts changing, and then as you get up above the so-called transfer frequency, you get all this structure. So it's a far more structured antenna pattern at high frequencies, which is great. It's much better for, say mapping out anisotropic gravitational wave backgrounds and things like that. The sort of downside is you start losing sensitivity as you get up to higher frequencies. So there's pros and cons to this. But the antenna pattern is no longer just this simple big quadrupole kind of peanut. It gets all sorts of structure at higher frequencies because of these finite arm length effects. So here, for example, is what the at 20 millihertz, this is what the LISA antenna pattern sweeping over the sky looks like. So you're running these little nodules of high sensitivity sort of over the sky. So that's that's what that looks like as well. All right. So we'll pause for a break in a moment, but I'll just get on to the beginnings of the next topic here. Eric, what do you think?
Let's take a minute and take a pause here to see whether there are any invite questions, right? I mean, maybe the right time. Are there any questions for Neil? That was a very nice animation you showed. I never saw that LISA antenna pattern at several frequencies. I didn't know it was so different. Yes.
Yeah, those are taken from a paper I wrote 20 years ago, which is embarrassing at this point. I was like, how did that happen? LISA had two incarnations, right? There was classic LISA, and then we went into the dark ages, and now we're back again. So, all these papers that I wrote when I was first starting out, just started my job in Montana just then, and I decided to switch from cosmic microwave background science, and I thought gravitational waves, that's where the next big thing's going to be, right? And so I started working gravitational waves, and I thought LISA's going to be awesome. And then it kind of went into the wilderness for a while, so I moved over to LIGO and Virgo. But now LISA's back, so.
So I see a question from Alexandre. Alexandre, your turn.
Yes. Hi, Neil. Thank you very much for the talk. And I just have a question concerning the sky localization. So you're showing that for ground-based detectors, you can triangulate and all these things. So I actually have two questions for you. The first one is, if you have 3 detectors or more, could you still get multimodality in the sky?
No, not really. In fact, there's several publications, including one with my student Kevin Schumann coming out very soon, where we're looking at that. So we've looked at, say, these two. There's 2 different plans that they're looking at in China for detectors, and when you include a second detector, it breaks in the same way, really, that, including Virgo breaks a lot of that sky ring degeneracy and that multimodality that we have with LIGO. It's broken for the space-based case as well by pretty much from like the vast majority of source locations. So having a second detector would be fantastic and it dramatically improves the sky localization that you can do if you had another detector up in space.
Okay. And so concerning also, so for ground-based, so for the Einstein telescope, for instance.
Right.
So actually, I'm a bit confused. How exactly because Einstein telescope are 3 detectors, but they are the same spot.
Right. It's exactly the same as LISA, basically. I mean, you get the modulation from the Earth's motion in that case. I mean, there's also the longer-term one of the Earth going around the sun, but the daily modulation of the Earth rotating, if you're looking at, say, a neutron star binary in ET is probably going to be detectable for hours, right? So the detector is going to move quite a bit during the time of the signal, and so you'll probably get pretty good angular resolution for something like a neutron star. But for a shorter lived signal, it's going to suffer from the same problems as LISA. So really, one would hope that we will have something like Cosmic Explorer in the US to go along with ET in Europe, so we can do the same kinds of things we currently do with, LIGO and Virgo in terms of localization.
Okay, thank you very much.
Let's see, some more questions.
There is a question from Louis. I'm not sure whether Louis wants to speak up because he has possibly audio issues. Maybe I can read through.
I can read it out. Right. Yeah. Yeah, so Louis is asking about, this sensitivity change with time for LISA. Is that a problem for detecting sources? And they do sort of go in and out. Absolutely, they're modulated. So yes, there's definitely times of the year when, for a particular sky location, for example, for a black hole merger, it'll be modulated. So there'll be times when, if the merger happens when it's over one of these nulls of the antenna pattern, we won't get nearly as strong a response. But we often are quoting sky average sensitivities for LISA to take that into account, right? So we integrate across the sky when we show those sensitivity curves. That's a sky average sensitivity. And there are some papers, a paper by Michele Vallisneri, and I forget who his co-author was on that, looking at the sky location, the sensitivities at different sky locations, and some are going to be better than others. So I actually see that modulation as a benefit, right? Because that's one of the key ways that we actually get information about where the signals are coming from. So and again, if we had more detectors, we'd have better sky coverage. So a second detector, like one of those Chinese detectors, would fill some of the gaps in the LISA antenna pattern. So that would be a positive development. So the parallax distance, yeah, they're too far away for a, I mean, typical sources are going to be way too far away for us to make a parallax measurement, but we are getting this sort of...
Isn't the time delay an analog to parallax in a sense, right?
It is. I mean, that is kind of what we're using, right? We're using that time delay, so it's sort of similar to a parallax, I guess. But the distance is mostly coming from the amplitude of the signal. But the time delay here has been used in the phasing, right, for the direction of arrival. We're not measuring a distance from that. We're measuring a sky location, the distance we get from the amplitude of the signal.
Right.
There's another question. If we add one instrument to LISA, we'll be able to cover all the sky. Well, again, if you orient the other detector in an appropriate way, you can organize it so that it's like, for example, if you put it say, leading the Earth by, say, 20 degrees instead of trailing the Earth, then its tilting over is going to be different from LISA's, so that you can actually get, it'll cover a lot of the holes. Another way that's really simple, the LISA, if I go back maybe and just show you that animation again, LISA goes around kind of in a cone. That cone makes a angle of 60 degrees to the ecliptic. But when you launch the constellation, you can choose whether that cone points up or points down. It's completely arbitrary. It's just a choice of the phasing of the orbits. There's no cost associated. And so if you were to do two detectors, if you face one up and face the other one down, you get essentially complete coverage then of the sky. So that's what we're advocating for the other detector should be oriented with the opposite 60-degree orientation, so that the two antenna patterns then are giving the maximum coverage. And it also significantly improves the sky localizations as well. So in fact, it was unfortunate when the decision was made to site the two LIGO detectors such that their polarizations lined up. It would have been way better for gravitational wave parameter estimation to have had them at 45 degrees with respect to each other. It was an unfortunate choice to line them up. It was chosen like that because they wanted to have as similar response as possible in the two detectors as a way to sort of distinguish between signals and noise, but that turns out not to have been really the best idea. But those decisions were made many, many years ago. But if we had it over again, we would orient the second LIGO detector at 45 degrees to the first one. Well, what I was saying actually does kind of make it a tetrahedron almost, but you can't, there is no orbit that will actually physically make it a tetrahedron that's equal arm length. You can do two different triangle planes at 60 degrees with respect to each other, but you cannot fly a tetrahedron without actually having rockets on them there is no orbit that does that, unfortunately. These are in Keplerian orbits, so we're limited by, yeah.
I actually find extraordinary that there exist orbits where a triangle is stable. Right?
Yeah, I believe this orbit was invented by Pete Bender, University of Colorado, and sort of the father of LISA. I believe Pete came up with these orbits.
Okay, well, I think we had quite a few nice questions.
All right.
Yeah, go
ahead. Yeah, let me just get started on this, and then we might take just a few-minute break. Let people... the father of LISA, Peter Bender. Yeah. Pete's still alive and active, so he's getting on a bit in years now, but he actually, the concept for LISA came up with discussions over dinner between Pete Bender, Ray Weiss, Charlie Misner, and I think Ezra Pound as well. There was dinner in Boston was where the idea was first discussed on a NASA panel that we're all serving on. So the history of LIGO and LISA actually go back to the 70s with Ray Weiss and Pete Bender. All right. Yeah, so I just want to get a little bit started on the basics of data analysis, and then we'll just take a little break and then come back. So really the foundations of what we use in our data analysis really goes back to Laplace and Gauss. So Laplace developed Bayesian inference, and Gauss developed maximum likelihood estimation. And in developing the sort of statistical descriptions here, Gauss introduced the normal distribution, which most physicists call a Gaussian distribution, and then later Laplace explained the ubiquity, why a normal or Gaussian distribution is something that we should expect to see quite often in the noise in experiments through the central limit theorem. So when you have a large number of small effects, they combine together to give you a normal or Gaussian distribution. So a lot of the mathematical underpinnings of what we use really goes back now over 200 years to Laplace and Gauss. So the basic idea is very simple, and of course Gauss developed this because he was trying to solve some problems with actual data, and so he invented the math needed to do these calculations. So for example, if we have some data, so we've got some data here, and I'm indicating some kind of uncertainties on the measurements of each of those data points, and then on the right I have some model. Basically what Gauss said is if you take the data, you subtract your model, the residual, which is the data minus the model, that should just be consistent with noise. So the correct model will be the one that after subtracting it from the data takes out the signal and just leaves behind noise. So that's the basic idea behind all of our gravitational wave data analysis, is we take the data, we subtract a model, and it has to equal noise. So not the most complicated mathematical manipulations here. So the data, D, is the gravitational wave signal H plus noise. So if you rearrange that, the residual, which is the data minus your model, should just be the noise, right? That's the idea. And in the example I've shown here, the noise was uncorrelated between data points. So these different samples here, I've done it as independent noise, and in addition, the uncertainty in each of these data points is the same. So in the vernacular of time series analysis, this is stationary white noise. Because the samples are uncorrelated between different times here, if this was time, not position, say, if this was just a time series, then if they're uncorrelated, then that is what we call white. And stationary means the statistical properties are invariant in time, so that the noise level is unchanging in time, and and in this case, the noise was just drawn from a Gaussian distribution. So each of the data points, the noise is just drawn from this normal distribution here. And so then the total noise is just the product of the noise in the individual samples. And that gets us this expression here for the probability of observing that noise. So if you substitute in that the residual should be following the noise distribution, so the data minus your model should be following the noise distribution, you end up with this expression here, which is just, and I've taken that product and put it up into the exponential now as a sum, so you just have the sum over your data points of the individual data di minus the model at each data point hi squared, and then divided by the variance here. And this would be the likelihood of observing that data given the model H. So this is the likelihood function that, that Gauss wrote down for the problems he was trying to solve. And with some slight modifications, this is the likelihood function that we also use. So the generalization is that if the samples are correlated, so that, for example, if the noise at instance I is correlated with the noise at instance j, instead of just having 1/2 sigma squared, instead we have this inverse of the noise correlation matrix appearing in there. And then out the front, we have the determinant of the noise correlation matrix raised to the... So this is just a multivariate Gaussian distribution, and the stationary white noise example I just gave you, so that's what C superscript SWN means. That's the case where it's just diagonal with all of the diagonal entries the same and just equal to sigma squared. And so that's a very easy matrix to invert. If you plug that in there, remember there's a little factor of a half sitting out there, you recover the example I gave you on the previous slide. So stationary white noise is just when you've got a diagonal matrix just multiplied by, like an identity matrix multiplied by an overall variance sigma squared. But the more general expression is this one, and that is the likelihood that we use in most of our gravitational wave data analysis. This quantity up here in the exponent is the chi-squared goodness of fit, and so it's just this, and here I'm using the Einstein summation convention, so this is summed over I and j. We write that typically using this little compact bracket notation like from quantum mechanics. So this is known as the noise-weighted inner product. D minus H here, so this is the residual inner product with itself, and this noise-weighted inner product for just general time series A and B is the inner product of A and B is just given by this expression. So that's the noise-weighted inner product appears all over the place in gravitational wave data analysis. It's the key quantity that we need to calculate. That's what we spend most of our time calculating. It's what dominates the computational cost of the analyses, is calculating these inner products. And I'll have more to say about that later. These matrices, if I actually had to invert this matrix, if it was a dense matrix and didn't have some particular properties like being, say, diagonal or at least band diagonal or sparse, then the computational cost of inverting this matrix becomes extremely large. And so in the case of, say, pulsar timing, we have a challenge because the data is, it's collected at sort of unequal time spacings. The noise is highly colored, and so we have these dense noise matrices. So there's a huge computational cost in inverting the matrices that we have in pulsar timing. Luckily, there aren't so many data points in pulsar timing because we only take observations every week or two over, say, tens of years. So there's like thousands of data points. In LIGO, we get tens of thousands of data points a second. So if we had to invert these matrices for LIGO, if they were dense matrices, it would be completely computationally prohibitive. So one of the simplifications that we have is if the noise is stationary, that is, if its statistical properties are unchanging with time, then, and it's a simple proof, you can then prove that the noise correlation matrix is diagonal in the frequency domain. And it's really easy to invert a diagonal matrix, right? Here, the diagonal entries would not be the same. Once we go to the frequency domain, these I's and J's refer to frequency bins. Previously, they referred to time bins. But now if I transform to the frequency domain, I and J now would be different frequencies. And of course, they're discrete because we have a finite observation time, so they would be separated by, each frequency is separated by 1 on the observation time. And then this quantity here, which is the noise spectral density, that's just what's appearing along the diagonal. But each term in the diagonal, and I'm using F here as the index, just to make it clear instead of I and J. So these are the discrete frequencies. And so this is the noise weighted inner product in the frequency domain. So now, instead of having to invert a big matrix and having a sort of an n by n sum, this just makes it an order n sum where n's the number of data points. So this is what's typically used in LIGO and Virgo analyses under the assumption that the noise is stationary. Whether the noise is stationary or not is something that we've looked at. It turns out, and this is covered in that LIGO Virgo data guide paper, the noise is stationary most of the time, as long as you look at reasonable short amounts of data, like a few minutes or so, it's quite stationary, except when it isn't. And when it isn't, there's often these noise transients, which we call glitches, which come in and mess things up a bit. But overall, the LIGO data is actually surprisingly, the LIGO and Virgo data are surprisingly Gaussian and pretty stationary. So this isn't a bad approximation. There are ways to do better that I'll get into tomorrow, but this is what's typically done, and it's also done in the sort of LISA data analysis that we're exploring right now. We're assuming currently that it's the noise is stationary, which isn't really going to be quite true, but it does simplify these inner products and makes them tractable computationally. One of the things we often do is we so-called whiten the data. What that really comes down to is multiplying the data by the Cholesky decomposition of the noise correlation matrix. In the frequency domain, though, that just comes down to dividing the data in the Fourier domain by the square root of the power spectrum, and then you can take it back to the time domain. And so we often show plots like this, which is the whitened data. So here's the whitened data actually surrounding GW 150914, I think, in the Hanford detector. If you take the data, you subtract the signal looks kind of scratchy because we've actually whitened the nice numerical relativity waveform here, and that whitening kind of adds in all sorts of weird features. I will get to that question in just a second. So the data minus the signal then should be consistent with the noise. So that's that's what Gauss taught us. You have your data, you subtract your model, you're looking for it to be consistent with the noise. So there's a question from Chiara in the chat: is Fourier transforming easy and quick? Yes, fast Fourier transforms have a computational cost of n log n, where n's the number of data points. So it's basically costs, roughly n. So the thing you really want to avoid is anything that goes like n squared. So the number of data points, if you're working up to the full cadence of LIGO, you're getting, and Virgo I think is even higher sampled, like 20,000 samples a second. LIGO is 16,000 samples a second. So you can see just with a few seconds of data, you've got tens of thousands of data points. Now, doing a Fourier transform sort of with tens of thousands or even hundreds of thousands is fine, but if I take 10,000 and square it, now I have a real problem, right? So you do not want to, you want to really avoid anything that goes as n squared. So you want all of the operations to scale as the number of data points at worst. And so these sums here, scales as the number of data points, transforming the data, scales as n. So the whole cost of a LIGO analysis or a typical LISA analysis using the frequency domain scales as the number of data points, whereas unfortunately for pulsar timing, the cost scales as the number of data points squared. So pulsar timing, it takes often several seconds to calculate a single likelihood. Whereas in a lot of the LIGO analyses, it's taking milliseconds or so or sometimes a bit longer to calculate a likelihood. So you really just want to avoid that n squared. Actually, that's something I want to get to tomorrow, and I'm becoming a big advocate for a whole new way of doing gravitational wave data analysis, which is to not use the Fourier domain, but to go to the discrete wavelet domain. And in the discrete wavelet domain, the cost of calculating the waveforms scales as the square root of n, and the cost of calculating the likelihoods scales as the square root of n. So instead of n squared, we get the cost down to the square root of n. So it's significantly faster than working in the time or frequency domain. And in addition, it allows us to handle non-stationary noise. So in the future, starting this year, all of the analyses my group does for both LIGO and LISA are all going to be done in time frequency. We're in the business of right now rewriting all of our codes to be in the wavelet domain, discrete wavelet domain, and they are blisteringly fast now in the wavelet domain. So I have a postdoc working with me on rewriting all our codes, so it scales as root n. I'm going to leave this slide up and take a 5-minute break, and I'm happy to take some more questions. And I've just got a slide right here that is talking about some of the challenges that we face in gravitational wave data analysis. So, for example, a signal from a generic eccentric spinning pair of black holes is a 17-dimensional model. So, and it can be quite complicated, especially at something like an extreme mass ratio in spiral. You also have to estimate the noise properties. That has to be inferred from the data. We don't get told what the noise is. We have to figure that out. And we have these noise transients, such as this big glitch here that impacted the data in the LIGO Livingston detector when we first saw a binary neutron star merger. So I'm going to get into all of that, but let's just take a little break. Yeah, I got a question actually first about the discrete wavelet domain. So, wavelets are basically, the Fourier domain is where you go in and you break everything up into like sines and cosines, right? Well, a wavelet is something that oscillates in some fashion, like a sine or a cosine, but then with an envelope such that it decays outside of that envelope, right? So it's only, it's both, it's localized in both time and frequency. So a Fourier transform is localized in frequency but not in time. These wavelets localize things in time and frequency, and by discrete, I mean it's actually an orthogonal. It's a complete set, just like a discrete Fourier transform. It takes n data points in the time domain and maps it to n coefficients in the Fourier domain. Exactly the same thing happens with a discrete wavelet transform. It takes, say, a time domain signal with n data points, it maps it to n coefficients in the wavelet domain, and it's completely invertible with no loss, right? So you can go back and forth between time domain and wavelet domain. It's completely, it's an orthogonal expansion in a basis, and so you can go back and forth between the two. Let's see, there's another hand up.
Hello? Hello?
Hello? Yeah, go ahead.
Thank you. I have a question regarding the term S with the noise power spectrum. I think that captures our understanding of all the noise characteristics other than the genuine gravitational signal.
Okay. Yes and no.
Oh, yes. Okay.
It does if the noise is stationary, then it captures the description, and if it's Gaussian, actually, it captures, because it's only the second moment of the distribution. So this actual plot here up in the upper right-hand corner is what's known as the amplitude spectral density. It's just the square root of that quantity, that S of F, and you can see here. Here's a typical spectrum from LIGO, and so it's giving you the sort of power spectrum of the noise as a function of frequency. If the data were Gaussian, perfectly Gaussian, and stationary, this would fully determine the properties of the noise. But unfortunately, the noise isn't perfectly Gaussian, and it's not perfectly stationary. So in practice, it actually takes a little bit more to really fully characterize the noise. But yes, if it was perfectly stationary and Gaussian, that quantity, the power spectral density, which is really just basically the power spectrum normalized in a particular way, would tell you everything you need to know about the noise, all its statistical properties. But in practice, the data isn't perfectly stationary or Gaussian.
Okay, but in a real analysis, the people make a best efforts to characterize the noise, whether
That's
it's
right.
really the
Yes,
so
and I'll get into that a little bit about how do we deal with the fact that noise isn't perfectly stationary and Gaussian, and we definitely take that into account in our searches and in our parameter estimation.
All right, thank you.
All right, so 5-minute break and return.
Yes, so we reconvene at 5:30 for me in 5 minutes. Okay?
Okay, see you back in a minute.
See you back.
Question. So in the chat, there's a question about how do you take into account non-Gaussianity. I probably missed something. No, you didn't miss anything because I haven't really gotten to that yet. So I'll have more to say about non-Gaussianity a little bit today, but more so tomorrow when I get into sort of more advanced aspects of the analysis, because that really is kind of at the cutting edge is how we deal with non-Gaussianity. So here's a bit more what you find in the typical textbooks, but I will get on to things that you won't find in the textbooks that have been written so far. Maybe I'll write a textbook, but that's a really crazy thing to do. Writing that review article with Joe just about killed me, so I'm not sure if I'm up for writing a textbook. Okay, all right, so onward to talking a little bit more about how we do these analyses. So the Bayesian way would be to invoke Bayes' theorem, which says that the posterior probability for a waveform, that says that given this data, the probability of measuring a particular waveform h given the data d is then given by Bayes' theorem by a product of the likelihood, which we've already talked about, which is the probability of seeing that data d given model h. There are various priors, which is your signal model, and then there's this normalizing factor, which is known as the evidence, right? So in a Bayesian approach, we would just simply calculate the likelihood. We'd have some priors on our signal model, and then you can calculate this normalizing factor, and then basically everything you want to know is then encoded in this posterior probability distribution for the waveform, right? So that would be it. And that's actually the way I like to do the analyses, but for various historical and practical reasons, the LIGO analyses have not been fully Bayesian. They're becoming more so with time, but I'll explain some of the challenges here. So the various signal types that we might be encountering are sort of well-modeled signals, such as a binary in-spiral or something like a continuous gravitational wave, maybe from a bump on a neutron star. Then there might be burst-type signals, which we, such as a supernova, core collapse supernova. Those definitely are modeled using various numerical simulations, but those numerical simulations still are probably missing quite a bit of the physics, so we can't really trust those waveforms completely yet. They give us some guidance, but they're not completely. You wouldn't use them necessarily as a waveform template model in an analysis yet. And then you can have all sorts of stochastic signals, such as phase transitions in the early universe, and that should be some kind of a maybe Gaussian noise type, but in this case it's actually a signal from the early universe. So these are the different gravitational wave signal types, or at least some of them, and those are essentially our priors on the shape of the waveform, right? These are all just give you, I'm showing them here in the time domain, but these models are basically priors on what the shape of the waveform might look like. Here that prior says it's a normal distribution with some spectrum, say. So for the different kinds of analyses, if it's a template for something like a binary in-spiral, then you actually have a mathematical model that comes from, say, post-Newtonian expansions or numerical relativity or some combination thereof to give you an expression for the gravitational wave as a function of a collection of parameters, and those parameters would include things like the masses and spins, say, of a binary system, and then you would have some kind of priors on those quantities. And that's a very strong prior because it basically is a delta function that maps the individual time samples or frequency samples onto this function. So it's a delta function mapping. For a burst signal of an unmodeled gravitational wave signal, we might model it in terms of some collection of wavelets. So here's a little picture of a wavelet. So some collection of wavelets can then be used to model that signal, and we have some kind of a prior on those wavelets. So in LIGO, there's a couple of, or a few different algorithms that use wavelets in different ways. Coherent wave burst and Bayes wave are two of them, and these are really wavelet describing the waveforms in terms of wavelets. One of those methods is a maximum likelihood method, and the other one is a Bayesian inference method. In the case of a stochastic signal, the prior on what the waveform might look like is actually given in terms of a multivariate Gaussian distribution, and then we might have some kind of a prior on what that spectrum might be. So I see some names on the participant list here who actually work on, say, calculating what the power spectrum might be from various processes, such as phase transitions in the early universe and turbulence and things like that, and cavitation and bubble nucleation. So there the models don't specify exactly what each time or frequency sample would be, but it gives us some kind of statistical properties of that. So that's what the priors would be on. So these are examples of what the actual gravitational wave signal models might be. And in the case of, say, a burst signal, one of the methods is to, as I was mentioning, break it up into a collection of wavelets. So in the upper panel here, each of these colored lines is a different wavelet. If you sum each of those wavelets together, you get the blue line. So there's this collection of wavelets, you add them together and you get this overall pattern here, and then you see this is a simulation where the red was the injected signal. You see we're able to recover the waveform by a collection of wavelets. Now this works for things that aren't just binary mergers. You can probably see behind me, I have a poster in my office which is from the first gravitational wave detection, and these reconstructions of the waveforms shown at the bottom of that poster are what this Bayes wave algorithm that I developed with Tyson Littenberg originally, this reconstruction of GW 150914. Tyson and I were looking at this reconstruction that day that the codes had produced, and we were pretty excited because it looked awful like a binary black hole merger to us. So that's the plot from what we produced that day. I've recorded on a poster for posterity here. And here, that same, just in a different color scheme. This color scheme on the poster, we shifted it to purple to kind of match the color scheme of the galaxies that they were shown in that that Aurora Simone made for us. Anyway, so this is a method where we actually end up with directly a posterior distribution. This is what these are. These are posterior distributions, probability distributions for the waveform. So the black is the high probability that the waveform actually followed that path, and it goes to lighter yellow here, which is lower probability that the waveform was there. So you can see these are probability distributions directly for the time samples. Now in the case when you have a model for that signal, so such as a template, then you can actually integrate out the individual time or frequency samples, and this delta function then maps this down to a posterior distribution, a likelihood now that only depends on the parameters. So now the posterior distribution is a posterior distribution for the model parameters like the masses and spins, and the likelihood has been, and this is what's known as hierarchical Bayes. This is a marginalized likelihood, and instead of now solving for the individual time samples, instead you're solving for the parameters of the waveform. And then you have priors on those parameters. So this is the normal thing that's used in LIGO-Virgo parameter estimation when you want to recover the masses and spins. We're actually trying out different parameters for the waveform and calculating the likelihood. But really what's happening is we've got this in-between mapping provided by those that do the, say, post-Newtonian calculations or numerical relativity or effective one-body or whatever calculations. They provide a mapping from the parameters to actually what the shape of the wave is. And then we sort of integrate that out. So then you can map out those distributions. And so I'm sure you've seen plots like this in a lot of the LIGO-Virgo papers where we have, say, these distributions for, say, mass 1 and mass 2 for the various, these are some of the first gravitational wave events, and we'll have our probability contours now for the parameters rather than probability contours for the waveforms. And similarly for the spins. So these, and I'm going to go into this a bit more later, these different spin parameters, chi effective and chi precession here, and we get these constraints on the spins as well, pretty weak constraints in this case. So these template-based analyses, we actually end up with these probability distributions for the parameters of the system. And we have similar distributions for like the sky location. I already showed some of those. So what is the physical parameter inference in the wavelet decomposition approach? Good question. Well, what you directly infer is the shape of the waveform, right? So it doesn't, the wavelet parameters themselves aren't very interesting. Each of those wavelets has, say, a central frequency and a central time. It also has a quality factor, which is sort of the number of oscillations in that Gaussian envelope of the waveform. None of those in themselves are particularly interesting, but you can take those waveforms and then calculate various quantities from them. You can calculate quantities related to energy. You can calculate frequency content directly from that reconstructed waveform. You can calculate the time frequency evolution of the signal directly from the waveform. So what we actually do is we take those waveforms and then we map them onto quantities that are, of some physical interest, like how quickly did the energy rise and then fall. So imagine sometime in the future, hopefully soon, we discover some completely unknown phenomena, right? So we get some signal comes in that's picked up by one of these burst searchers, so coherent wave burst picks it up, and then we do inference on it using both coherence wave burst and then the Bayesian Bayes wave analyses, which will then give you the waveforms, and then we can extract all of these things like these time scales, energy scales. Then you can do the detective work of trying to figure out, well, what kind of thing in the universe could have created a signal like that, right? So it doesn't map you directly to a model because it's a model-free analysis, but it does map you to things like time scales, energy scales, durations, things like that. And hopefully you can then do some detective work to figure out what could have produced it. A good example of that is if you take gamma ray bursts. So gamma ray bursts, when they were first discovered, people got things like the spectral slope of the gamma ray burst. They would get the durations, and they classified them into short, long, and hard, soft, where the short obviously was referring to the duration. The hard, soft had to do with the spectral slopes, and those actually, we now believe, separate into, some of them come from binary neutron star mergers. Those are the short, hard, I think, and then you've got the long, soft, or whatever. We think those are maybe collapsars. So, you can then start trying to fit a model to what you're seeing in that waveform. So there'll be a fun game we get to hopefully play when we discover something totally new. Now, if you were to do this in a fully Bayesian fashion, and say you were using templates for a a binary black hole merger, then there's at least 17 dimensions that you need to cover. And this, you have to map out this sort of likelihood surface to then get the posterior distribution. It can be multimodal. We've already seen that in some of the examples for sky localization. It can be quite expensive sometimes to generate these models and perform these likelihood evaluations. So trying to map out this whole space can be a very expensive undertaking. In the LIGO-Virgo analyses, we get a vast amount of data, but there's very few signals, detectable signals in there. So we're sifting through huge amounts of data for rare signals. So we only get a signal every few days, which is great. We didn't used to have any, but still, that's a tiny fraction of the time that we actually have a signal in the data. So like sifting through that huge amount of data is difficult. So we basically, just like they do at CERN, we sort of filter and have triggers. So we have much more basic low latency analyses that don't give us a detailed answer, but they kind of tell us whether there's a chunk of data is actually worth looking at more carefully. And so we get these triggers that we then analyze in more depth. With LISA, we'll actually have a much smaller amount of data, but the data will contain millions of overlapping signals. So that's a completely different kind of challenge there. And then with pulsar timing, as I've mentioned, we have unevenly sampled data with complicated noise properties, which makes the computation of the likelihood extremely expensive. So generically what we tend to do, and this will probably even be true in the LISA analyses as well, is we start with a search phase where we do various maximizations and ignore various parameters at first, and then we follow up with a more fully fledged Bayesian parameter estimation after we've found some useful triggers to focus in on. So searching for signals, and I'm just going to give a really basic version of it here, and this is switching to a sort of a frequentist approach here. So you have some detection statistic that can be pretty much anything. We'll typically use something that relates to the signal to noise, which I'll get to in a moment. And then you have, say, two hypotheses. Was the data just noise, or was the data noise plus a signal, right? So you've got hypothesis H0 and hypothesis H1, and under those hypotheses, the probability of measuring a certain detection statistic, which is shown along the horizontal axis here, under the noise hypothesis, you would expect the distribution to be peaked at low values of this statistic, whereas under the signal hypothesis, you would expect it to peak at higher values, and as the signals get stronger, this peak should move over, right? So with stronger signals, you get greater and greater separation between the noise hypothesis and the noise plus signal hypothesis. And then, you could imagine defining some kind of a threshold lambda star such that for values of this detection statistic above that threshold, it's favoring the hypothesis that says we've also got a signal in the data. So that's the basic statistical setup. And so you have to have some kind of a statistic here. And then we talk about the various kinds of errors. I think the general public has been hearing a lot about this over the last year with the pandemic, hearing about false alarms and false dismissals with things like COVID tests and whatever. And we have the same things here in gravitational wave data analysis. The stakes aren't quite so high. We've got false alarms and false dismissals, and you set your threshold where you want to balance either false dismissals or false alarms, and so we usually set things based on a false alarm rate. So if we were in this idealized case, and I will get to the non-ideal case, but if we are in this idealized case of stationary Gaussian noise, we saw that the likelihood takes this form here, where that's the noise-weighted product. So I'm just reminding you what we had earlier. Then for these two hypotheses, under that simple case of stationary Gaussian noise, we just end up with, if you take the likelihood ratio between the signal plus noise hypothesis and the pure noise hypothesis, if you just plug that into this expression here, so one of them has the h in it and one of them has h equal to 0, that means that you get this quantity here, lambda, would be the likelihood ratio, and this would be a good detection statistic, and it's just given by the inner product of the data with the template and this factor of the template with itself. So this would be then the likelihood ratio detection statistic. So that's the sort of textbook detection statistic that we might use in gravitational wave analyses. In practice, we don't exactly use that because the noise isn't perfectly stationary and Gaussian, and I'll get to that a little bit, but this would be in the sort of theorist version of how the analysis goes. So if you fix a false alarm rate, so if you say, okay, I only want one fake signal every, 100 years, because I don't want to be making a claim that we've detected gravitational waves when we really haven't, right? So you might want, in the case of gravitational waves, we're being very conservative. We don't want to have, a false alarm. In the case of disease, you probably would err more towards not wanting to have false dismissals. You don't want someone going around infecting everyone. If you've given them, you told them they've taken a test and you've told them that they're not positive, you'd want to err in the other direction. So in the case of gravitational waves, we want to be very careful not to claim a detection when there isn't one. So we fix a false alarm rate, and what we do is we maximize this ratio over all possible signal parameters, and then this yields something called the Rho statistic, which I'll describe in a little bit more depth. So if you maximize that first with respect to amplitude, that's where the Rho comes in here. It's the scaling. And then if I can just take the derivative of this with respect to Rho, and I find that this Rho statistic is given by the inner product of the data with a unit normalized template, where the normalization is done with respect to this noise-weighted inner product. So this then becomes the detection statistic, the Rho statistic, which is related to the signal to noise. And the way it's related to the signal to noise is you take the expected value of that signal, the expected value of that quantity when a noise is present, divided by the root mean square value when a signal is absent. So you take the expectation value, and then you divide it by the root mean square when a signal is absent, and it's easy to show that this comes out to being the inner product of the signal with the unit normalized signal, and then that's the square root of, since that normalization factor is just the square root of h with itself, this is then the signal to noise. So this is something you see all the time quoted in gravitational wave analyses. We're always talking about the signal to noise. So the signal to noise ratio squared under this inner product is just given by this integral. I can go between sums and integrals here of the gravitational wave signal in the Fourier domain, absolute value squared divided by the noise, and this is the signal to noise ratio squared. So this is where it comes from this simple detection statistic. Now, we no longer really use this primarily in the analyses because the noise isn't perfectly Gaussian, and so we use things like what's called the new SNR statistic, which is introduced by Bruce Allen back in 2005, which also takes into account the way the signal would build up in frequency. So you could look at the details of that. So we use a variant of this statistic now that is more robust against non-Gaussianities. I'm going to say a bit more about non-Gaussianities tomorrow, but more in the context of parameter estimation. But these kind of modified detection statistics that are more robust against noise are now used, and we also do a lot of background estimation I'll get to in a moment to actually, we don't just take the theoretical distribution for these statistics, we actually Monte Carlo them on the data to actually see what the distributions look like. So if we just went back though to this very idealized theorist version of analysis, we would have, if it was Gaussian noise, then this row statistic would be Gaussian distributed. The null hypothesis would have this distribution. So these are the distributions I was showing earlier. The detection hypothesis would have this distribution where it gets offset by the signal to noise ratio squared. And so then if we set ourselves a threshold, we can get our false alarm and false dismissal probabilities given by these error functions. And then you can, decide then, we don't really use an SNR threshold in LIGO. We use a false alarm rate threshold. So the false alarm rate threshold is given by the false alarm probability divided by your observation time. So for example, if you only wanted a false alarm 1 in a million years, then over an observation time of 1 year, that would be a false alarm rate, so a false alarm probability of 10 to the minus 6, which is about a 5 sigma detection. And that would correspond in the ideal Gaussian case to a signal to noise threshold of about 5. In practice, it's higher because of several things. One is that we maximize over a bunch of parameters, and also because the noise is not stationary and Gaussian. So we end up with somewhat larger thresholds. And anyway, we do it in terms of false alarm rates anyway, not directly in terms of signal to noise. So the standard method for doing a LIGO search then, or LIGO-Virgo search, is you've got all of these parameters, like the masses and spins, for example, and so you lay out a grid of templates, but you want that grid to be fine enough so that you don't go missing signals, right? So you want to make sure that if there is a signal there, you've put in a template that's close enough to it that it will actually give you a large inner product. So you can calculate the fractional loss in SNR by this quantity called the match. So if you have templates with parameters x and y, the match is just the dot product of the two templates divided by their normalization. So this is a quantity that runs from -1 to 1. And you don't you want this match to be very close to 1 because you don't want to miss signals. So you can then say, okay, if I'll tolerate a certain loss of signal to noise, that kind of gives the fineness of this mesh. If you make this mesh too fine, then the computational cost is going to be too high, right? So it's a bit like if you go fishing, you want your net to have small enough holes that the fish don't get through. But if you make those holes too fine, then your boat would come to a halt dragging this, this net behind it with a really fine hole. So you want the holes sort of big enough so the fish don't get through, but wide enough so that the boat can still pull it. It's my fishing analogy, trawler analogy for gravitational wave data analysis. So we go trawling through the data. So in the case that we want to Taylor expand, so for example, if two signals have parameters that are quite close together, you can Taylor expand this and you get this expression here under the Taylor expansion, which then defines a metric on parameter space. So here are the parameters are xi, xj, and it's actually a Riemannian metric. And this metric was first written down in the context of gravitational waves by Ben Owen, and then working with Sathya Prakash to develop this idea. So this is this Riemannian metric on parameter space, and you can define volumes and things. And so if you want to cover this sort of d-dimensional parameter space, then the number of templates you need is the volume of that space divided by the volume of parameter space that's covered by each template out to this level of match that we require. And so if you set a minimum match of, say, 0.97 or whatever, and then you can calculate this number of templates, and it's easy to see that this number grows geometrically with the dimension of the space for any kind of lattice. So the more parameters you have, the number of templates you need grows very rapidly. So for example, if you wanted to do a search for something like an extreme mass ratio in spiral using just a template lattice with, say, a match of 0.97, it would require, the number here is vastly larger than all the number of atoms in the universe. So completely computationally out of reach to do a search like that. So you have to come up with some tricks. In the case of LIGO, LIGO-Virgo grid searches, typically we only search over 2 or 3 parameters, say the masses and maybe some combination of the spins, and we've come up with all sorts of tricks to maximize over the other parameters. So these grids tend to be, tens of thousands of points, so the computer filters against that grid, and then, it rings off against, if there's a signal in there, then it will ring off against that signal at some point in the grid. So we basically filtering the data against these banks of templates. Now, to reduce the cost of this search, you can always maximize over at least 3 parameters, sometimes more, and I'll just go through how that's done. So you can always maximize over the amplitude or distance, because you take this unit normalized template, which defines some reference distance, which I'll call d bar. So there's going to be some distance at which you get a unit, SNR of 1, right? So that's your unit normalized template. Then when you actually, the template that fits the data then is given by just at a distance d, is just given by d bar divided by d times the reference template. And so then when you can just read off the distance from this inner product of the data with the reference template. So you get the distance for free just by this scaling. So the distance is a free parameter, or the amplitude, the overall amplitude is a free parameter. So you don't have to search over that. That cuts down the search by 1 dimension. There's an overall phase offset that you can always search over. And what you do is you just generate 2 templates, one with phase 0, and then one with an overall phase that's pi on 2 out, so like a sine and a cosine. And then you just calculate the inner product of the data with the cosine template, the data with the sine template, square those, take the square root, and that's automatically now maximized over the phase. And you can see how that works. For example, if the signal looks like h naught e to the I5, this is the overall phase here, then the inner product of the cosine template just comes out as the cosine of the phase. The inner product with the sine template comes out as the sine of that phase. If I square this, if I square this, I get cosine squared plus sine squared, which is 1. And so I've automatically taken out this overall phase. So we don't actually have to worry about the overall phase. We can just get that by doing these quadratures here. And finally, we can also, if we're working in the Fourier domain, we can also maximize over time offsets, because in the Fourier domain, time becomes periodic. So we can just convolve the Fourier transforms and automatically then wrap our template around in time and try out all possible time delays. So we use the periodicity of the Fourier transform to our advantage here, and by calculating this quantity, we get all of the different time delays. And so this is then the inner product as a function of the time offset. And we just get that by, you take the Fourier transform of the data, the Fourier transform of the signal, weight it by the noise, and then take the inverse Fourier transform of that, and that now gets you a time series, which is a signal-to-noise time series. You can see then if you were to, if your data, if there was no noise, for example, and the data was offset from your template by t0, then this maximum happens when that offset is t0. You can just pop that in there and see that that's where the this Fourier transform is going to light off, becomes a delta function at delta t equals t0. So that allows us to search over all possible times just by doing a Fourier transform. And we usually break this up into chunks So we might be searching over like, of order 20, 30, maybe a minute of data and calculating these SNR time series over those chunks because the data is fairly stationary over those times. And plus we want to, maybe even work with shorter chunks so we can get a very quick trigger if there is actually something in the data. So we could send out an alert then to look for an electromagnetic counterpart. So this can all be put together into a single quantity, this complex quantity Z, which is the inner product of which you calculate using a complex Fourier transform. And so you calculate this quantity, you maximize over the time just by finding the maximum of the absolute value of this quantity. That's the rho statistic. The angle, the phase angle is maximized as given by the argument of this complex quantity. And then the distance, because this is unit normalized, is just d bar times rho. So the larger this rho, the further away it was. So this is how you automatically find the time of arrival, the overall phase, and the overall amplitude of a signal in each detector is got just by calculating this one quantity. So that speeds up the searches significantly because we've taken out a bunch of the parameters so we don't have to search over them. They're just maximized over analytically. So here's an example of how things are done in LIGO-Virgo analyses. This is the so-called PyCBC search. There's other searches. There's now, I think, 4, maybe 5 template-based searches. PyCBC was one of the original ones, one of the early ones. So basically, you take the data in each detector, you calculate the power spectral density estimates for each of those detectors, and then you make one of these template banks. You filter the bank against the data in each detector individually, so you don't do it as a network, but you actually filter against, say, the LIGO detectors, in the LIGO-Hanford detector, LIGO-Livingston, and Virgo, so that's done independently for each detector. You calculate this, you find the maximum of this chi-squared, or this new SNR, so that's related to that rho statistic I was telling you about. You perform coincidence tests now. You demand that triggers in every detector must have triggered at the same sort of masses and spins with an appropriate physical time delay. It's got to be within the light travel time between the detectors, so that throws out a lot of the triggers. You can also check for phase, that the phases make sense as well. This is all described, I think, quite nicely in this LIGO-Virgo data guide paper. Goes through how this coincidence step gets put together. So basically, you filter the data in each individual detector, and now you're making sure that anything that's ringing off in one of the detectors is consistent with what you're seeing in all the other detectors. And so if you do get a coincidence in trigger from all the detectors, this now is a candidate gravitational wave signal, and here's this business of checking that time shifts are also consistent, and this whole workflow is tested by using simulated signals, and we also use time slides, which I'll get to in a second here, to actually calibrate what we would expect the distribution of these statistics to look like. So you don't rely on them being Gaussian distributed according to some theoretical distribution. We actually Monte Carlo it to see what the distributions are. So, I think I've just got, I'm just going through the steps here. I forgot I had all those little, so I had some questions earlier about, how do you handle the non-stationarity and the non-Gaussianity? Well, the non-stationarity, part of it is because we've got the overall sort of power spectrum sort of drifts up and down with time. So one way to get around that is if you work with short enough data segments, then at least over that short time interval, the data, the power spectrum is pretty much constant over that short amount of time, less than a minute or so, or even minutes. So you work with short data segments and estimate the power spectrum of each of those short data segments. Now there's other things, noise transients or glitches, and those add in non-Gaussianity. So what that's going to do, it's going to throw off those distributions. So instead of those different hypotheses having nice Gaussian distributions, because of the glitches, the null hypothesis is going to have like much more of a tail to it, a much longer tail than a Gaussian. So we deal with the glitches in a couple of different ways. The LIGO and Virgo instruments, in addition to producing the gravitational wave strain output channel, there's also tens of thousands of environmental monitors that are also operating. So there are things like microphones and seismographs and all sorts of electrical magnetometers and things like that. And if we see disturbances in some of these environmental monitor channels, we can veto that data because we're like, wow, there was a big earthquake, or there was a plane went overhead, or something like that. And then, you know, we do correlations. Is there any correlation between a blip that occurred in our gravitational wave sensitive channels and some of these tens of thousands of monitor channels? So we can veto things. So we have various kinds of vetoes that say, no, that data was probably corrupted by something. And then, in addition, what we do is not all of the analyses do this anymore, but traditionally we would do these time slides where you take the physical time stamp of the data, say in Hanford and Livingston, and then you actually artificially shift the data in time. And here it's getting shifted around on a circle. So by the time you've shifted the data by more than 10 milliseconds, if something's coincident in the two detectors, it couldn't be a gravitational wave if gravitational waves travel at the speed of light, because the time delay between the two detectors is at most 10 milliseconds. So once I've shifted the data by, say, 1 second, there should be no way that that was a gravitational wave signal that was causing a common response. So what you do is you rerun your analysis with different time delays. And that gives you then a distribution that tells you like what the null hypothesis is, right? Because that should have killed the signals, so it should just be noise now. And so by trying out lots of different time delays, you can actually Monte Carlo what you would expect to be seeing if there was just no gravitational waves there, and that forms your reference distribution for the null hypothesis. And then if you see something above that, you're like, that could be a signal. So an example, first of all, of some of the gremlins that can mess it up. Here's a rogues gallery taken from the Gravity Spy, which is a website where citizen science people come in and help try and identify these different kinds of noise transients. Here's just some of the types of noise transients. These are in time frequency maps. This is time across the horizontal axis, frequency vertically here. And so you see these little excesses, these yellow excess power. They could be gravitational wave signals, but they, in these cases, they're just various kinds of glitches, and we give them names: blip glitches, chirp glitches. Well, that's actually a chirp. That's a signal. We have, here's a Tomte glitch. We've got wandering lines. We've got scattered light. All these types of blips and whatever in there, which we try and veto, but some get through. And so here's just from an example of this. This is the Monte Carlo distribution as a function of this new SNR statistic. And we showed in that first paper two distributions, one where this very loud event was actually included in the time slides. And that actually led to a very large background because it actually rang off against random glitches in different time slides. If you sort of exclude the region around, if you just remove that little bit of data, you then get this much quieter background. And then you see that this is the background distribution on a log scale, whereas the event's way out here. So we had an extremely strong greater than 5 sigma detection here because it was well outside the this background distribution. And then similarly, if you see for gravitational wave transient catalog 1, which is a combination of the observations from the first and second LIGO observing runs, we've now got the first part of the third observing run. here are our Monte Carlo, say, background distributions, and then you see the various events here which stand out above that background. So if anything was down here in this gray region, we wouldn't consider it significant. But if we have things out here, above that, then those are significant events. So that's how we sort of Monte Carlo and handle. We don't assume the theoretical distribution of the noise. We actually Monte Carlo it to find what the distributions are. And let me just see. I think that's it for today. Yes. So tomorrow I will continue on and get into the Bayesian parameter inference and some more advanced topics. But we've got a bit of time left for some discussion and questions. So the last part of today was all about searches. So happy to take questions about anything that I've talked about today.
Thank you very much, Neil. Are there any questions for Neil? I'd like to just take the opportunity here to mention that just before Neil's lecture tomorrow, you have the possibility to join us on Gather Town. I've invited my colleague Agata Trovato, she's working on the Gravitational Wave Open Science Center, which is the website that distributes LIGO and Virgo data. And if you're interested, we can explain you how to download the LIGO and Virgo data and run a few tutorials that actually reproduce what Neil just shown. So you're very welcome to join us there.
Yeah, my plan was, if I'd been in person in Paris, I would have done some hands-on analysis sessions using the tools from the Gravitational Wave Open Science Center. There are some very nice tutorials in the form of Python notebooks, and they load in the data for you, and then they go through the various steps, make some nice graphs along the way. And you can either just run those tutorials as given, or you can mess around with them, right? Because they're notebooks, and you can load in different data and sort of see what happens, or you can mess with things a bit and see what changing some of the settings does. So it's not just a static thing, it's something you can explore. This paper that I was telling you about, the LIGO Virgo data guide, it comes with a notebook that reproduces most of the graphs in the paper. So you can actually go through and start with the original LIGO data and reproduce most of the results in the paper. And you can, like I said, you can mess with it.
Okay, so I see questions in the chat. So I have a question first that was sent privately to me. What time is the meeting tomorrow? So it's an hour before the lecture. It's at 3 p.m. for European time. So I'd let you convert to your time zone. So there is a question by Paul. Do you want to read it, or do you want to speak up, Paul? Maybe not. Can you do, okay, no mic. Can you do actual physics with the blips and noises? Interesting question.
Yes, very good question.
So I complete the question, right?
Yes.
For instance, learn about detector passive activity, or is it just exploitable, not exploitable in any way?
Absolutely. In fact, there is an entire group in LIGO called the Detector Characterization Group, and they use these, well, they study these noise transients and other impacts on the data, and they try and do detective work to figure out what it is that's causing these, right? So over the years, they've actually discovered often by seeing correlated activity happening in some of these other witness channels, these monitor channels, they've found correlations between various things that are happening in the detector and then these transients we see in the data in the gravitational wave channel. And they've been able to actually track down quite a lot of sources of noise. And then people have, the instrument folks like David Shoemaker, Ray Weiss is always in there kicking the tires, and Rana Adhikari, one of Ray's former students, and a bunch of others get in there and they actually make changes. The teams at the detector sites are able to then, swap out some electronics that might be causing some problems or whatever. So they learn a lot about the, operation of the detectors. Now, once all of that has been done, there are still a bunch of these blips and things that we don't know yet what their origin is. And so those remain for us to deal with. But the idea is hopefully we can, trace more and more of those back to something that's happening in the detectors, and then learn something about, is there something in the mirror coatings? Is there something, or there are some like defects in the suspension cables that are releasing a little ping or something like that. So they're learning a lot about the detector science and how to make quieter detectors. One of the new activities that's becoming quite a big activity now in that group is using various kinds of machine learning, because you have this huge number of detector channels, right? And trying to look for correlations, especially nonlinear couplings between these different witness channels and what's happening in the detector is very difficult. And so they're using convolutional neural network techniques. There's an algorithm called Deep Clean, which is using deep learning to correlate between what's happening in some of these witness channels and yeah, so it's a major part of detector commissioning and detector improvements is what the detector characterization group does, where they're forever trying to track down these noise sources.
Okay. Any question for Neil?
I remember, just while I wait for the next question, so you all know Ray Weiss and his former student, Rana Adhikari, who's at Caltech. Before Advanced LIGO and Advanced Virgo came online, Rana was telling me, "Oh, don't worry about those glitches. There won't be any in Advanced LIGO. It'll be perfect. It's going to be nice and clean." I was like, "Yeah, I don't know. That doesn't seem likely." And of course, it actually is worse. In the advanced detectors, they've got the overall noise level down, but the problem is, as you lower your overall noise level, you expose more and more of those little things that wouldn't have been a problem before. So, in fact, the number of glitches and the amount of non-stationarity is actually gone up. And then, in a conversation with Ray, Ray's sort of old-fashioned in his way of doing analyses, and he thinks that a lot of the statistics we do is sort of, a little bit kind of black magic to him. So Ray's comment to me is always, "We don't need your fancy your fancy statistics. We just need to build better detectors." So they keep on wanting to make the detectors quieter and less glitchy. The trouble is that's not happening. So we still need our fancy statistics to handle it. So.
Right. I would have a question there. So you've been presenting, this way of Monte Carlo, of simulating by Monte Carlo this the background that we have.
Right.
But can we imagine another way of doing this without this Monte Carlo? Are there any alternative way of?
Yeah,
this is an expensive, right? This is expensive. This takes time to do. Is there a more direct way to do without this?
Yeah. So what I went through the classic analysis here, which is PyCBC is based on the very first analyses that were developed for LIGO. there is another. Why am I forgetting the name of it? I'm having a name blank. So there's PyCBC. Anyone online, please help me out. The other main match. Sorry, which one?
GST-Lao.
Yes, GST-Lao. So, and maybe I've gotten the wrong way around, but anyway, one of them does not use these background time slide things at all. It's based on a, it works just directly off a theoretical likelihood calculation, but a much more complicated one than the one I described. So it's based on some statistics, on some search statistics, or a combination of them. When you put it all together, it forms an overall likelihood that has a mathematically predicted distribution. They've checked it, and it corresponds even in non-Gaussian noise. They found that it does indeed follow the distribution they expect, so they don't even check it anymore. So that does no time slides. It's purely a advanced theoretical calculation of this product of likelihoods. So one of them does not use time slides at all anymore, and one of them does. And it's true, the time slides are very expensive. The time slides are used by coherent wave burst, and I'm pretty sure it's PyCBC that still uses the time slides, even though I could have them the wrong way around. It's one of them, GST-Lao, or I always forget which one's which. But one does not use time slides at all anymore.
I think you're right. Well, I think maybe we are getting to a time here where students are a bit tired and had a long,
long day.
Long day with lectures.
Time for dinner and a glass of wine.
Exactly. Especially from Asia, I think there are a number of students here that are connected from Asia. It's late, very late for them. So I believe we should close here for today, and I'm surely tomorrow. I think you'll have more questions after a good night of sleep.
Right, great. Well, I will see you all tomorrow.
Thank you.
Good.
Thank you.